Everyone, let's talk about the Quadrature Hybrid, or the 90-degree hybrid, as the book says. So this is, you can see, a 4-port network here. 1, 2, 3, 4. And it's comprised of, we have an input impedance here, Z0, coming in. So these are the ports coming in. We have basically 1, 2, 3, 4 segments here. These here are also matched, Z0, but these two segments here, you'll notice, have an impedance of Z0 divided by the square root of 2. And there's a very good reason for that, as we shall show later. So over here, I have written out the S matrix for this particular device. So you notice it's a 4-port network, which means we are not subject to the constraints we saw earlier about matched, reciprocal, and lossless. We can, in fact, be all of those things at once now for 4 ports. So right off the bat, you notice I've matched these off-diagonal elements here, right? So that is reciprocity in action, which will have to be true for any just sort of passive line like this. You notice also I've drawn it as kind of like a looking down on a microstrip line here. So the width of this line will kind of represent the characteristic impedance here. And it's just easier to look at it in these terms because we don't have to deal with those sort of parallel wire depiction that we normally do in our schematics. So just looking at this device here, we can notice a few immediate properties are going to fall right out. For example, it's symmetric here, right? So if I feed a signal here and something comes out, it should behave exactly the same no matter which port I am injecting a signal into. So for example, the reflection here should be the same as the reflection over here, and the transmission from here to here should be the same as from here to here, or from 1 to 3 should mimic the behavior of 4 and 2. So the first thing we can do is we notice all these diagonal elements, they all have to be the same thing. S11 is equal to 2, which is equal to S33, which is equal to S44, right? Because if I flip it or rotate it, or I flip it horizontally or flip it vertically, I get exactly the same device, which means there can't be any difference in these terms. Likewise, from 1 to 2 is the same as from 4 to 3. So what that is going to impose, S12 is equal to S34 or 43. So I'm going to write 3, 4 here. So because there's no 4, 3 the way I've written it here. And S13 should match S24. So S13 is equal to S24 here. All right, so what I'm going to do now is rewrite the S matrix like the following here. All right, so I'm going to have S11, 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 and then S11, all on the diagonals there because they all have to be the same value. I'm going to still have S12, S12 here, and we're going to have S13 and S14, S13 and S14, like that. So we saw that S23, oh yes, so 1 to 4 should also match 2 to 3 here. So S14 is equal to S23. So a signal coming in and then kind of transmitting out should mimic this side over here. So here's S14, so this is now S14 here, and S14 as well. Okay, so you see all these diagonals here are all the same value. And then we've got, let's see, S12 is the same as S34. So that is 1, 2, and which is going to be the same as 4, 3, S12 like that. So these guys are now all the same. And finally, I have S24 is equal to S13. So that's an S13 and an S13. So originally, we had 16 elements, but reciprocity meant this was reduced to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it went down to 10 because all these other guys had to match. And then we imposed all these other conditions, and you find at the end of the day there are only 4 unique values in this entire network here. We have S11, S12, S13, and S14. So if I can calculate all of these S parameters here, I will have essentially solved for my entire scattering matrix. So the way we're going to do that is, again, we're going to just pretend to excite this network under even and odd symmetry and just kind of create an equivalent circuit to see how much reflections we get and how much transmission we get out the other side. And from that information, we will then be able to derive the S parameters or the elements of this S matrix. So let's go ahead and do that now. Okay, so you notice I've drawn out the equivalent circuit for the even mode excitation. Okay, so I have my quadrature hybrid here. I'm going to excite it port 1 and 4 with an even voltage. So they're gonna have the same magnitude, same sign, as opposed to the odd case, remember, would be the same magnitude but opposite sign. And by the same argument, because they are symmetric here, I can essentially bisect this entire thing down the middle and say no current will flow at that midpoint down the middle of this line. So something else I also kind of forgot to mention is this here, this total distance is a quarter wavelength, as well as this distance here. Okay, so that is also lambda over 4. So we're going to need to make use of that information as we go through this derivation. So let's get started here. Okay, so what we have is an incident voltage here, V1, with a value of V0, which is equal to V4. And we're also imposing the condition that V2 and V3 plus are equal to 0, which simply means I'm not exciting it from this direction here. So from the S matrix, we can now say V2 minus is V1 plus times S12 plus V4 plus times S24, which, if we write that out, will just be V0 times S12 plus S24. And likewise, I have a reflected voltage that's going to bounce out over here, which is V1 plus times S11 plus V4 plus times S14, which will simply evaluate to V0 times S11 plus S14, like so. Okay, so what we're going to do now is a similar derivation like we did last time. We're just going to, this one turns out to be the easy case first. So all I have to do is calculate the equivalent impedance looking down this entire network here, which is going to be a few little sub-steps, right? So first things first, I'm going to draw a little input here. I'm going to call that ZA. And then I'm going to have another guy here. I'm going to call that ZB. And then there's going to be a final Z-in over here. So I'm going to call that Z-in or ZEQ. So all I have to do is calculate this and then roll it back to calculate that and then roll it back again. So just looking at this circuit here, I'm going to say Z sub A is, remember this is Z0 here, Z sub 0. So I'm going to have Z0 in parallel with this stub. So I'm going to say Z stub like that, which is the equivalent input impedance looking down that little shunt stub with an open circuit on the end. So to calculate that, I'm going to say Z stub is, just remember our transmission line impedance equation. I'm going to get Z0, so I can get out my notes here, ZL plus JZ0 times the tangent of beta L divided by Z0 plus JZL tangent of beta L. So first things first, you notice the length of this stub is lambda over 8, right? Because originally we chose it as lambda over 4. And then we said right here at the middle there can be no current. So the total length of that stub is half of lambda over 4 and thus lambda over 8. And if I put in lambda over 8 for my beta L, these tangent terms both become 1. Okay, so what I will get then is simply Z0 times the quantity of ZL plus JZ0 divided by Z0 plus JZL. Also, the load down this stub is this little point here, which is infinite. So I'm going to take the limit as ZL approaches infinity. And what you end up getting is simply Z0 divided by J. So that's the equivalent impedance looking down an eighth of a wavelength stub, okay? So that now implies, I'm going to calculate ZA is going to be 1 over Z0 plus J over Z0 to the minus 1, just parallel of the two. And so I will then get Z0 times, or just divided by 1 plus J, like that. Okay, so that is the equivalent input impedance looking down this little parallel network over here. So now I have to roll back and ask, what is the equivalent impedance looking down into this little quarter wavelength piece of transmission line? So that means I'm going to get ZB is again going to be another transmission line input impedance, only the load is going to be ZA, and my characteristic impedance is this Z0 over square root of 2. So remember, what you'll get is essentially you get the line impedance squared divided by the load impedance, or in this case, the line here, because that's for a quarter wavelength line. You always get this. So the line is going to be this Z0 over square root of 2 squared, and then ZL is Z0 over 1 plus J, like that. So we do a little bit of rearrangement, and what you'll find is you get 1 plus J times Z0 over 2. So it's a few steps, but each step is relatively simple and straightforward. So now I have to put that in parallel with another stub. So I'm going to get Z in. So my total input impedance looking down this thing here is going to be Z stub in parallel with ZB. So we'll just write that out, and I will get Z stub J over Z0 plus 2 over 1 plus J times 1 over Z0, and then 1 over that. Okay? So that means I can factor out the 1 over Z0. So I'll get a Z0 times, and you get J plus 2 over 1 plus J, 1 over all of that. So fun fact, if you do this calculation, this whole thing becomes 1. So my equivalent impedance looking into all of that is simply Z0. So it's matched. So by simply choosing these particular lengths and that particular characteristic impedance, I have created a matched load. So that implies V1 minus is equal to 0. Because there are no reflections in this particular case of excitation. So now I'm going to plug that into up here, and the implication is immediately just falls right out. S11 is equal to negative S14. Okay. So now what we're going to do is we need to figure out the voltage that's transmitting out the other side. So that turns out to be a little bit more complicated. If you want to use straight transmission line theory, you can, but it turns out it's a lot easier to go backwards than it is to go forwards in this example. So the book offers an interesting derivation based on the ABCD matrix. So let's go ahead and work that out now. So again, I'm just going to kind of draw my little network here. Only I'm going to draw this as essentially a series block or series connection of 3 blocks, kind of like that. Okay, so let's just call this, I don't know, like A, B, and C or something. Or you could call it 1, 2, 3, X, Y, and Z, it doesn't matter. The point is, there's an ABCD matrix here, CD, and then another ABCD here, and another ABCD, which means the ABCD for this entire cascade is found by just multiplying them all together. So there's a nice little application of that little bit of theory for 2-port networks. So what is the first one here? Well, this guy here, this first ABCD, is a network that's going to look like this. So I have some little shunt admittance Y, which was found, remember, is just our little stub that was 1/8 of a wavelength. So that means the equivalent impedance of this shunt here was, what did we get? We got Z0 over J. So that implies the admittance of that little shunt is equal to J over Z0. So then you ask, what is the ABCD matrix for this? And it's in the book. So you get an ABCD matrix that is 1, 0, Y, 1 for a little shunt admittance like that, which simply becomes, what do we get? 1, 0, 1, J over Z0. So that's my first ABCD, and it's incidentally also my third one, okay? So 2/3 of my work was just done there in that step. So now I have this guy here, which was simply a length of transmission line, beta L. And again, this is in the book, and it has an ABCD matrix to go with it, which, if you remember from the textbook, was cosine beta L. Then you get J, so the characteristic impedance here was Z naught over square root of 2. So I get a J Z naught over root 2 times sine of beta L. And then over here, I'm going to get a 1 over that. So I get a J root 2 over Z naught times sine of beta L. And then this becomes another cosine beta L. Now we've also chosen this to be, again, quarter wavelength. So if I put in a quarter wavelength, all of these trig terms simplify. And what you end up with is simply 0, 0. So the cosines go to 0 and the sines go to 1. And then I'll just get J Z naught over square root of 2, and then J root 2 over Z naught. Okay, so the ABCD matrix for this entire little cascade is simply, we'll just sort of write it out. I'm going to get something like this. 1, 0, J over Z naught, and 1. And then I'm going to get this guy, 0, 0, J Z naught over square root of 2, J root 2 over Z naught, and then you repeat this guy again, 1, 0, J over Z naught, 1. So that is the ABCD for this entire cascade, which it's a little tedious. You can go through and you just do the matrix multiplication. So, you do this product plus that product becomes the first entry. And then you do this plus this, and then this plus this, and then you do it all again on the remainder. So it's a little bit of tedious. So I'm just going to kind of skip to the end. But I totally pinky swear that this is the result you get. You'll get a -1 J Z naught over, and then I'll get a J over Z naught here, -1. And then the scale factor out front here will be 1 over square root of 2. So that is the ABCD matrix for this entire cascade. And then all I have to do now is calculate the corresponding S parameter for this particular little 2-port network. Right? So there's going to be an S21 or S12 corresponding to this. So remember, this is kind of a fictitious representation of what's actually a 4-port network here. So this S21, I'm going to call it S21 prime, really, so that it's not confused with this matrix here. This is this sort of fictitious 2-port network that we've done for the even mode of excitation. And so I have S21 prime is, by definition, in this case, is V2 minus over V1 plus, which implies V2 minus is going to be S21 prime times V naught over here. So that means if I can calculate the transmission coefficient down here, then I have my V naught here, and I can then find a relationship between S12 and S24 here. So this is what I'm after, is that term there, which will relate these terms over here. All right, so remember also in your book, if I do a conversion between A, B, C, D, and S matrices, there's just a simple table lookup. So I'm going to say S21 prime is equal to, let's look up my notes here. I'm going to get the following. 2 divided by, and you get A plus B over Z naught plus C Z naught plus D. Like that. So that is just the straight up conversion from this ABCD matrix to this S matrix for this cascade. And when you just shove in all of those terms here, it works out pretty well. So you get 2 over, you get a -1, J Z naught over Z naught. So yeah, so let's see if we can do this by hand here. You'll have a -1 plus J plus J again, and -1, kind of like that. So you get sort of like a 2 over J minus 2, or 2, sorry, 2 minus 2J. So it's basically 1 over 1 minus J, and then there's a 1 over square root of 2 that gets in there, which if you then simplify, at the end of the day, all the dust settles, you get negative 1 over square root of 2 times 1 plus j, if you work out all the math there. Okay. Hopefully I didn't make any typos there, but that's the answer you get when you just plug into here. Okay, so what that now tells me is the following. I'm going to go back to my V2 minus here is going to satisfy this. So I have V2 minus is equal to V naught negative over square root of 2 times 1 plus j, which is equal to, so just going to plug it right into here. So that's my V2 minus is going to equal that. So I'm going to get V naught times S12 plus S24. So you see the V naughts cancel, and you essentially have S12 plus S24 is equal to, so I got it here. Yeah, here it is. Negative 1 plus j over square root of 2. So you notice we started off, let's go back here, we had 4 unknowns that we're trying to figure out what they relate to. And I have now created 2 equations here. So here's one equation, and then here is the other equation. So there you go. So I created one equation and another equation for my unknowns. So if I had 2 more equations, then I can uniquely satisfy all of these parameters. So what you obviously do is you do the odd mode analysis, and you do the exact same derivation. So you can just follow along with that if you really want to, but we can just kind of skip to the end. That if you do the odd mode here, so I'm just going to write it here, odd mode analysis. And what you'll find, you'll get 2 more equations, and the following results just kind of fall out of it. You'll get S11 is equal to S14, which is equal to 0. That falls out immediately. And then you'll find that basically S12 is equal to, or not equal to, sorry, they're close. S12 is equal to minus j over the square root of 2. And then my S13 will be negative 1 over root 2. So there's a little phase there that accumulates. So when you put all of that back in at the end of the day, you'll find that you get the following for your scattering matrix. So there'll be a negative 1 over square root of 2. And then you'll have 0, j1, 0, j, 1, 0, 0, 0, 0, 0, 1, j, 1, j, 0, like that. Okay, so that is the scattering matrix for this quadrature 90-degree hybrid. So what you kind of see is a signal comes here and it will split 2 ways here, and there'll be a phase shift between them. So that's what the J's here are kind of all about. So you saw with the Wilkinson power divider, a signal came in and 2 signals came out that were both in phase. Now it's the 90 degree here is because one signal essentially comes out straight, and another one now has to travel that extra little distance, so it's 90 degrees out of phase here. So you can see that's obviously got some interesting use so that's why it's called a quadrature as well. So you have 2 sinusoids, equal split, equal power, just 90 degrees out of phase of each other. So if you ever take digital communication theory, that idea of a quadrature becomes very, very important in any sort of digital communication system. Okay, so that is how we create an equal split of power, but with a nice 90 degrees phase shift between them. And so that's why you see you have the J1s here. So the 1 over root 2 represents the half power. This J here represents the 90 degree phase shift between the ports. Okay, and of course, everything sort of behaves equally well backwards as well as it does forwards, right? So a signal come here will split, or a signal come here and split, and vice versa. Okay, so but that is a very common and useful device in microwave engineering for all sorts of wonderful practical applications. And here is the scattering matrix associated with it.